So let me introduce Fabrizio Andreatta, who will give his second talk on Eichler-Shimura morphisms, and he will focus today on the non-holomorphic case.
Yeah. Okay. So thanks a lot. Let me try to remind you what we are trying to do. So what we are trying to do is the following. So giving a classical weight. So we defined yesterday sort of an Eichler-Shimura isomorphism between certain cohomology of the Siegel variety with the full level n, which is prime to p, with some algebraic etale coefficients that we had to dualize because the comparison map goes from the dual of the Tate module to the Rham cohomology. So there's a duality floating around. And so that is isomorphic with the Rham counterpart that can be defined on xn. And here again, we have algebraic the Rham coefficients. Here we consider our variety C over QP with Rham. So we have this, and we want to deform this p-adically into families for a reason that I tried to hint at yesterday. And so I try to sort of divide the problem into three sub-problems. The one is to make sense of this etale coefficients, okay, where k now will be not a pair of integers, but maybe, as we saw yesterday, some analytic character of a two-dimensional torus. So what do we do with these algebraic etale coefficients? And then we had a question 2 and a question 3, because on the Rham side, as we saw in the holomorphic case, we first of all are forced to work with not the full Siegel modular variety, but with the smaller things. Yesterday we worked with the neighborhoods of the ordinary locus for the Ivahoric level Siegel modular variety. And then we also have to make sense of this the Rham coefficients again when the weight k varies p-adically. What does it mean? Okay. Okay, so let me try to write in parallel the two things that we did yesterday and that we want to do today, which is related in this case to also what George discussed, but especially to the theory that Vincent developed in his first paper, the Duke paper on the higher Coleman theory for JSP4. Okay, so let me start with with the input that comes from the geometry of the Hodge-Tate map. Okay, so maybe I'll try to squeeze in here also. Sorry, I forgot. I should have done it before. So we have the Hodge-Tate map. We have xn over Cp, and we have a GZP cover. And one way to get around the geometry, for example, problem 3, as I said, explained yesterday, is to fix actually the zero-dimensional Schubert cell, okay, in the flag variety. And today, instead, actually, we will work with the closure of the Schubert cell inside the flag variety associated to the element in the Bell group that is realized inside the symplectic group in this way. So this is what before George called S2, so that in the character group, so it permutes the second and third entry in this 4 entries where you consider either the lines or the rows or the columns, so this matrix, for example. And so I will work with this geometric object on the flag variety side. And let me actually get into more details on how to describe this Schubert, this subvariety of the flag variety. So here, see that I'm not working with the compact support or with the complement of closed. It's really a proper thing. And actually, so as George explained, so this closure GW bar, so this classifies Lagrangian subspaces of VP dual. That was the model that sort of we used to define the flag variety, that contains just one vector, which is this vector E4 dual. Okay, so you see, if you fix such a space, then we have that the quotient Z modulo the span of E4 dual, well, that is contained in the orthogonal of E4 dual, which is the span of E4, E3, E2. We mod out by E4. So we see that we get actually a line inside this 2-dimensional space. So in fact, this tells us that this Schubert variety, in this case, it's simply a P1. Okay, so the simplest 1-dimensional, the simplest that we can consider. And actually, there is one specific Lagrangian subspace that we considered yesterday, the one spanned by E4 dual and E3 dual, which is the rational one that defines actually the point infinity inside P1. Okay. Okay, so that's an explanation of this geometric object, so we understand very well. Then let me continue with the subdivision in 2 of this virtual sheet of paper, where we discuss what we had yesterday and what we do have today. So yesterday we considered the Ivahori subgroup of GZP that was floating around in defining, for example, the level of the Siegel variety we were working with, but it was also used to induce representations. Okay, so on the tal side, we use this Ivahori subgroup. And in this case, instead, we work with the parahoric associated to the following parabolic subgroup. It's the Klingen parabolic of G, I call KL. So this is simply using the presentation that I did of the symplectic group. So using the symplectic form in the way that I wrote yesterday. So these are matrices of this form. In G. So you see here we have the Borel, and we are actually enlarging the Borel by adding something extra, which is actually if you take this permutation that we considered before, it can be defined using that one actually. And the group that we work with is actually the Klingen parahoric subgroup that contains then the Ivahoric subgroup. These are matrices in GZP such that A reduces to matrices in the Klingon parabolic modulo P. Okay, so that's something slightly different from what George considered in his previous talk, where he always worked with the Ivahoric level structure. And that's something that actually was mentioned also in the discussion after his talk, where he mentioned that, for example, when you want to define the overconvergent coefficients, eigenvarieties, if you work with the Ivahoric level structure, you have really two UP operators that are floating around. If you allow yourself to increase the level structure, like we do here using the Klinger parabolic subgroup, you have just one UP operator that is floating around, that is in its notation 1, p minus 1, p minus 1, p minus 2, okay? And at the expense of actually having a smaller character group, okay? But we will come to this. And actually, this is the setting that appears in the first work of Vincent, so that's why I'm stating today, okay? So at the modular level, so yesterday, continuing this subdivision, we had the subquotient of this Galois cover given by this perfectoid tower, which is the SIegel variety with the Ivahoric level structure. And today, instead, we mod out by the Klingon parabolic. So I'll just write the X sub KL N CP that maps to X and CP again. And this actually classifies, at least in the open part away from the cusp, principally polarized abelian surfaces plus full level N structure, plus actually a flag of subgroups of the P torsion, H1, H2, H3, which is equal to the P torsion, with the property that, I mean, generically, this is rank P, and this is actually rank P cubed, and it's actually the orthogonal of H1. So it's fully determined by this H1, in fact. Okay, and so the construction of the sheaves on the Rham side and the cohomology, the Rham cohomology that we compute and so on, and the classicality result that Vincent has proven is exactly for this level Shimura varieties. Okay. Now coming to question 1, what are the etale coefficients? So yesterday it was simply an induction from the Borel to the Ivahoric of some character chi, okay, where chi varied on a two-dimensional weight space, okay, where here you have an action of the Ivahori. If you identify this with the fundamental group of this SIegel variety, defines the local system that we are considering, or the variation, the p-adic variation of coefficients that we are considering. So here the character varied in a weight space that is associated to a two-dimensional. So we can simply write ZP star squared, okay? So this is the plus part, and then, well, so the generic fiber, if you want. So this, let me simply write associated to. Okay, so it's the generic fiber of this formal scheme. Sorry?
Sorry to interrupt, Fabrizio.
Yes.
B is the ZP points of the parabolic, B? The Borel,
yes.
These are the ZP points?
Yes. Sorry. Yes, absolutely, yes. So here, so that was actually, I'm coming back to what George discussed after his talk. You see, we want to induce, I'm coming back, sorry for this. So I want to induce not from the Borel, but from the Klingen parabolic, okay, to the Klingen parahoric. And actually, if I do that, you see that the characters of the Klingen parabolic drop by 1, and there is only one character, so the character group. So in this case, so the weight space, maybe I'll just write W prime. So this is the weight space for the characters of the Klingen parabolic, okay? This is actually one-dimensional. So this is simply associated to ZP of ZP star. So it is one-dimensional. And the character actually, if you write your Klingen, okay, it's simply the projection on this vector, okay, the algebraic characters. Now you can do it analytic and so on. And in this case, the coefficients will be simply the induction from characters that might be now analytic on ZP star of the Klingen points of ZP to the Klingen parabolic of K, okay? K is our character W prime. Okay, and again here you have an action of the Klingen parahoric because of this induction. And you can also do actually locally analytic induction if you are, I mean, depending if your weight is not analytic, you can do various things. You can take the dual and get the distributions. So on both sides, get also spaces of distributions. Taking duals. So on this side, actually, we had, let me simply write this dk etale, and here you have some dk etale. And these actually are the coefficients that yesterday I constructed in a different way and was denoted by yesterday it was denoted by WK etale, maybe Joule or something. Yeah. Okay. So yesterday it was denoted this way. And here we have again this definition, but mind that we are missing now one dimension. We're simply varying things and the weight space in one direction. Okay. So that's for the etale coefficients. From the point of view of the geometry, okay, so we proceed like yesterday, and we take simply the inverse image of things in the flag variety that reduce to this P1 modulo P, okay? And if we mod out by the Klingen parahoric, that defines a certain subspace that again I denote by bigger, less or equal to 1. This simply to remember that we work over FP here. So when you work with the local analytic characters, you need to take smaller neighborhoods, and this is actually defines So yesterday it was the inverse image of infinity. Now I'm stopping writing the analogy between the two. So this defines a neighborhood of the component of X Klingen and of the Klingen level structure SIegel variety, such that the first piece of the filtration on this abelian surface that is floating around in our modular problem is isomorphic to mu p. So that's sort of a generalized ordinary locus. So it's a locus where the p rank is exactly 1. And actually there is one component of this p rank 1 locus where the level subgroup that we are fixing in our modular problem is exactly the multiplicative part coming from the fact that we have p rank, p rank at least 1. So it could be also p rank 2, so it could be completely ordinary. And in that case, again, we require that each one is containing the multiplicative part. Okay, so it's this component. Okay. Okay, so what is happening on this locus? Why is it so relevant by the pi-Hodge state map? So on this locus, and now here actually I'm going to define so yesterday, remember that when we defined the Rham coefficients and their variations, we had two cases. One was the Hodge variation, where we just varied the things related to the Hodge bundle, okay? And I explained how that related to work of myself, Adrian, and Vincent. Here I want to do the same remark, so the Hodge case. So on this locus, what do we have? Well, so via the Hodge state map, so remember we have the Hodge state map, okay? And this is actually isomorphic to, say, if you go to the perfectoid level, it's isomorphic to VP, okay, dual, and we have our comparison that goes to this new integral structure inside the differentials. And actually, if I mod out by P, and actually I say tensor, I go to the perfectoid level, I have here two elements that so I have elements E3, E2, E1, and we are demanding on this locus, okay, that the kernel of this map is contained in the span and then the quotient, so let me simply write this, the span of this so that defines a line, and I also have an element E1 dual that is all elements actually spans. This whole space, because remember that if we sort of extend scalars of this map alpha Hodge state, this big omega was defined in such a way that the map became surjective. So since E3, E2, E1 dual, so these elements must span everything, okay? And actually, so the span of this, the OX plus P infinity span, is actually a line bundle. So I have a line bundle, that in fact descends to omega A modulo P. And we have on this locus that I'm considering this maybe up some small finite etale cover. I have this line bundle. I have this omega A modulo P, and I have the quotient which is actually spanned by some specific element, which is the image of this A1 dual. If you want, it's also the image via this map, alpha of Tate or D log of a small canonical subgroup that deforms this mu P. Okay, so we have this structure. Yeah, that's what I want to focus on. So this is a rank 2 thing, modulo P. See, this is a rank 1 thing. I have another rank 1 thing, and somehow I have an FP reduction, some kind of marked section, which is the image of this A1 dual coming from the Hodge-Tate period map. Okay, now, so we can play the game that we played yesterday, and in fact, if you take the space of on this locus again, so these are elements, so this classifies simply elements of the dual of omega A, let me call them rho, such that rho modulo P is 0 on this line bundle L that we have, this extra structure that we have on this line bundle. And then we want that the evaluation of rho on E1 dual is an element in FP. Okay, again, modulo P. Everything makes sense, modulo P. Then you see you have an action of GM. In fact, you have an action of ZP star 1 plus PGA, simply scalar multiplication on omega A dual. And I can define this omega K. And let me add a 0 here, actually, for a reason that will become clear in a moment. So K is any analytic weight over this one-dimensional weight space that we defined in this Klingen situations. So these are the functions on this thing here. That transform under the character K, that being analytic extends to a character of this open of the torus, okay, under the action of ZP star 1 plus PG. Okay, so this is the sheaf constructed by Vincent in his Duke paper. This is another way of getting it. Okay, and actually, if K2 is an integer, one also defines omega K here. I don't know how to. You want to denote. You can twist by the determinant. So let me write like this. and you get slight variations. So here we do an algebraic construction, so we can twist this slightly, this p-adic construction with an algebraic construction, and in fact get slightly more general shapes that at some point will appear later on. Okay, so here we cover then the sheaf that was introduced by Vincent. So it's a simple operation that we are doing. And now I want to explain you how to, using the same idea, get the Rham coefficients. And then, except for the comparison map, we'll have the three ingredients that will actually allow us to define this Eichler-Shimura map in this context for k that varies in this one-dimensional weight space. Okay. So also in this case, we can refine the Hodge filtration that was usually we have on the full SIegel variety by considering a rank 4 vector bundle, which I call HA sharp, that contains this modification of the integral structure of small omega. Okay, so this is a rank 4 OX plus vector bundle with the property that the quotient by this rank 2, this omega A, is again rank 2. And actually, we can play the same game as above. So I can define V0 of this HA sharp dual, L dual, A one dual. Okay. So again, this classifies sections. Maybe I can change name, gamma of HA sharp dual, such that gamma on L is equal to 0 modulo P. So it's exactly as we did before. And the second thing that we demand is that gamma evaluated on this element is actually in FP star. And then scalar multiplication again defines an action of ZP star 1 plus PGA. And I define, so I leave some space here on the left, because then I can define actually WK de Rham for every K analytic character on this one-dimensional weight space. I can define WK, maybe I'll add a 0 for the same reasons that I did before, WK0 de Rham as the functions on which this ZP star 1 plus PGA acts via the character K. Here you see I can, of course, project down to V0 of omega A dual, E1 dual, and that at the level of functions gives us an inclusion of omega K0. And in fact, this is only the first piece. Actually, of the Hodge filtration on this WK0 de Rham, and but it will play an important role. That's remark 1. And remark 2, we also have a connection. That goes from this WK0 de Rham to WK0 de Rham tensor omega 1 on xn, well, again, Klingen, let's equal to 1. Sorry about this. And so we can form the Rham complex of this. Which consists of four steps, okay? And also in this case, I don't want to get too much into this, but using this description of these spaces as functions on the spaces that can classify sections and so on, one actually can describe the induction and the distributions on the etale side by a similar construction. So you classify sections on the dual of the p-adic modules that satisfy certain properties, and then the map half-Hodge state that goes from the dual of the p-adic module to this to the Rham cohomology actually will give us a comparison map. From decay etale to this space dk0, the Rham tensor O be the Rham plus, which is exactly the analog of what we had yesterday. So yesterday I ended my lecture having this on my whiteboard. Okay. And here again, if k2 is actually a non-negative integer, one can twist this etale representation by an algebraic one. And also on the Rham side, you can twist by classical Rham coefficients so that you get actually make sense of this comparison map and of these things. Also, when you don't simply have 0 as I had before, but also a k2, but I don't want to get into this. Okay, so far so good, hopefully. So what I want to do is actually give an explicit description of this spaces. First of all, wk, the Rham, and also, actually, simply one for the moment. We will speak about the Rham complex in a moment. So in the Horic setting and in the Klingen parabolic setting, okay? And actually the description will be rather similar. So let me deal with the Horic setting. So we fix some open of this open that was floating around, okay? And then actually the function of this space that I introduced yesterday of we had some HA dual, rho 1 dual, rho 2 dual is actually defined the plus structure by the following variables. I hope it will be clear in a second. Remember that in the Horic case, we fix two sections, okay? So there is a modular relation that I'm not going to describe. I will tell you how it comes. And actually, we have to sort of the universal sections that this space describes is given by the following matrix multiplication. So this is some fixed, well-adapted basis of HA dual, so dimension 4. X is simply the matrix x1, 1, x2, 1, and similarly for Y. And then remember that we had certain requirements on our, so making this column matrix multiplication, we get indeed two sections as a combination of gamma 1, gamma 4. So we had two conditions in the definition of this V0. So one condition was that these two sections are actually paired to 0. So they are sort of via the symplectic pairing. And actually this comes into the relation, okay, the fact that the relation that I'm not describing. So I'm not, let me not spell this into too much this. And then we had other two properties. And the other two properties were that these sections should sort of pair with this marked section rho 1 and rho 2 in a special form that was the Borel modulo, essentially a Borel that on the diagonal had the elements in Fp star. And actually that is given by the fact that there is a relation between the entries of this matrix and the zi's that appear. So you see I'm defining a partial blow up that takes into account the extra condition appearing in the definition of V0. Okay? So very, very explicit. Okay? And here you have an action of actually a left action of GL2. And you have an action when you write these things on the duals of the opposite Borel of GL2. And now, so I hope it's still readable, but I'd like to have things on the same blackboard. So the space VK the Rham, if you fix an analytic weight, well, this is simply, it has sort of the structure. So it's the subspace of functions, the functions I've written to you in this very explicitly, where the action of this parabolic, this B minus, is through the character of the Borel, which is given by this K underline, okay? And remember that, so K underline is a pair of elements which are characters of ZP star. And actually you can write things down, and this will be simply of this form, K1 minus K2, determinant of X, K2. Now this makes sense because of this requirement. So it makes sense to apply these characters to those variables expressed in the ZI's, okay? And then you have the functions of weight 0, of course. And well, you have a part. Okay, so here, there's no hope to have everything on the blackboard, so you enlarge the normal side. So you have a part which is given by this. And then you have another part which is explicitly described like this, where B1 is the determinant of the matrix that you get by taking the first column of X and the first column of Y. So this is an explicit description of actually of the sheaf omega K that I introduced yesterday, that I, with Adrian and Dilson, introduced. And actually, the rest, the yi's and the bi's, actually, let me maybe change color here, are what makes this the Rham sheaf interesting. And in fact, the degree in this Y1, Y2, and B11 defines the Hodge filtration. So degree 0, you just get omega k. Then you have degree 1, you take polynomials in these three variables of degree less or equal to 1, and so on. Okay. Let me describe for you what happens in the Klingen case. Klingen case. So we have a similar description. So now we have less variable actually, and so I'll let you figure out the variables. But let me stress how this K2, the Rham, looks like. Okay, so in this case you have a similar thing. So you have x1 kk, and then you have the sum. So remember that K2 was an integer. You have the sum for I goes from 0 to K2 of R plus x1, x12, x11. Then you have y1 sorry, I'm missing a piece. Sorry about this. So well, never mind. Let me write as I was writing it. So it's R plus x12, x11, and then we have y1, x11, y12, x11. And then instead, you see, instead of having the behavior that we saw here, where you have convergent power series in this, due to our algebraic assumption in K2, we are actually multiplying this by B11 to the I, determinant of X to the K2 minus I. So it's a smaller thing. And again, there is a Hodge filtration, which is defined by the degrees of the B11, Y11, and B12. And the degree 0 part is exactly an explicit description of the sheaf that Denson has introduced in his Duke paper. Okay, so very good. So now I want to give a description in terms of these generators of what the Gauss-Manning connection does. And since I was sure that it was running out of time, I prepared a small PDF file where I describe this. So let me stop sharing. And actually, let me share a different thing, which is this one. Okay. Oops, sorry about this. So here you see I have this description of this sheaf omega k, and you see that these W, I, J, H, S are exactly the generators in the, here we are in the Bahoric case. You have a description of the generators, but also actually you have a similar description of the generators of this WK. Also in the Klingen case, if you specify that K2 is an integer and this H that appears here is less or equal to K2. in the Klingen case. Okay, so these are the generators. And now, actually, there was a question yesterday about Verma modules. And indeed, you can describe these sheaves by an infinitesimal action. You see, you still have on these variables a right action of the symplectic group. And if you let the negative roots act, you can span things in terms of the highest weight vector, which is actually this one. And there are three specific negative roots that actually appear when you want to compute the three differentials that come into the definition of the Gauss-Manin connection. So the Gauss-Manin connection maps WK de Rham to WK de Rham tensor the differentials of the Siegel threefold. This is a threefold, so omega 1 is actually three-dimensional, and you can identify at least infinitesimally the tangent space with the opposite unipotent of the Siegel parabolic, and these are actually the three roots, the three generators of this indexed by their roots, actually by the sort of other torus acts. So let me not get into this. Now, if you simply plug in this infinitesimal action of the symplectic group of this verbal module using the right action on the variables, you have these formulas. And I like to draw attention on three terms. One term is here. So you see that these three derivations. So the filtrations is given by E plus J plus H equal to N gives the graded N part of the Hodge filtration on these spaces. And you see that these derivations actually increase one way or the other by one, the weight filtration, as you would expect by the Griffiths transversality. But they do it in different directions. You see, the first one here goes into the J direction, and here it goes in the I direction, and this one actually goes into the H direction. Okay. And you see, if you are on the fraction field, so to speak, of some open of the weight space, in the Ivahoric case, all these elements that appear in front, they become invertible. And that simply implies, in terms of the Gauss-Manin connection, that in fact your the Rham complex, at least if you consider the union of all the filtrations, okay, I mean, remember that the WK is the p-adic completion of the union of all the filtration. So if you consider this subspace, so this tells you that if you take the Rham complex, this is actually represented simply by one single thing, because you can sort of, everything else is in the images of the Gauss-Manin connection, so to speak. And it allows you to compute the Rham cohomology in terms of a very simple BGG complex, okay? Instead, if you are in the Klingen case, you have a rather different behavior, because you see what happens since K2 is an integer, so K2 minus H is not invertible anymore, as we were in the Ivahoric case, where this coefficient became invertible on the fraction field of some affinoid of your weight space, and it actually vanishes exactly for H equal to K2. So this gives a contribution to actually the BGG complex that computes the Rham complex for WK de Rham. Okay. So it's so a bit vague, and also it's a bit unfair that I'm using a PDF file. But let me try to move to the conclusion. So let me go back to my whiteboard and see, even if here I was a bit vague, let me tell you what is the outcome. Sorry, wrong screen to share. Oh, sorry, here it is. So outcome of these computations of the differentials. The first outcome is actually in the Ivahoric case. And it tells us that if you take a space K, which is defined over some wide open, defined by some algebra B, okay? So this in order to have what was mentioned in one of the questions on the first day to one Esteban, to be able to write these big etale coefficients into finite subfiltrations with finite coefficients, so that you can compute very effectively the etale cohomology. Then the interior cohomology, maybe Vincent wrote it like an H bar, in this case, of X, Ivahoric, and CP of dk, it's a D, sorry, etale. Well, this, thanks to work of Stevens and Urban, it has a very nice slope decomposition. Here, I'm just, at least if you don't take the interior thing, so I'm restricting them to the image of the interior thing. This actually maps to the H0 on this locus where everything happens. Maybe actually I have to take smaller loci. So here, let me take a dagger, meaning that I take even smaller neighborhoods to make this whole construction work. And actually this BGG complex that is floating around, that I told you that actually reduces to just one single term, gives, it's simply becoming, if you take finite slope part, it's becoming like this. And here actually I'm, that's where I'm using that the etale cohomology is the interior one, because on the right hand side, due to the difference of toroidal and minimal compactification, a problem that already appeared in the previous talk, I have to use cuspidal coefficients, and actually tensor field -3 of the classical Fontaine ring of Rham. That immediately paves the way to define, if you take Galois cohomology of QP bar over QP, a definition of the dual exponential mapping in families, okay? So here, the map is simply, this map is simply obtained by taking the map on cohomology from the map on coefficients that we had before, okay? With two remarks. First of all, the first remark is that we have a very nice slope decomposition here, thanks to work of Stevens and Urban, maybe even Hansen. And on the right-hand side, remember I told you that we can control the Rham cohomology of this dense subspace of this the Rham coefficients, which is given by taking the union of all the slope, the Hodge filtrations, okay? But the UP operator in this case, actually, it's very divisible by P on the quotients of the Hodge filtration. So classes in this Rham cohomology of small slope, you can prove they lie actually in the Rham cohomology of this dense subspace, where you have the union of the filtrations, okay? And then you use these computations of the differentials to prove that then the Rham complex is represented by simply by this sheaf, at least if you remove some coefficients, because you remember you have K1 minus H appearing and so on. So if I go to the fraction field of B, you get such a map, and actually it's easy to see that it is compatible with the classical comparison. So what happens instead 2 minutes more in the Klingen case? So here we don't know really what kind of cohomology we should consider. Interior, compact support, I don't know. We don't know that there is a good slope decomposition. So here is actually the big question marks that we still have not analyzed with Adrian. I think Marcus Saviso is thinking about this. But I don't know what's happening here. So of course, if you don't know where the comparison map from where it should leave, it's not really clear that the map that I'm going to describe makes sense. But so I want to set up the kind of cohomology that I'm considering in order to get to actually the Rham complex of this WK the Rham that we had before. Okay, here the space where we are, it's on this X Klingen less or equal to 1 that we had before. Okay, and we would like to take less or equal part. Okay, and maybe here we are tensoring with the Rham. So here I should make sense of what it means to take a small part of this. But let me just make a motto, and the motto is that we can define if you take the cuspidal part. This has a slope decomposition. Again, simply because the UP operator that we have in this case is the other one, 1 minus p minus p minus p squared. It's very divisible by p on the quotients of the Hodge filtration. So again, it's enough actually to have a slope decomposition on the filtrations. And the filtrations are actually made up of varied pieces that are the sheaves that have been studied by Vincent in this paper, and for whose sections actually H0 and H1 admit a slope decomposition. And in fact, again, here, if our weight K is defined over some wide open, defined by some B. Actually, here I forgot I should have also a K2 that was floating around. Sorry about this. I'm hurrying too much. Sorry. And the computation that I showed you before tells us that if you work over frat B, this is actually represented by a BGG complex, of which you are computing the cohomology that consists simply of 2 terms. And then if you tensor also with B the Rham, you can sort of make sense of this. It's the following: omega K plus 3, 1 minus K2 minus D. tensor field minus 2 be the Rham. Mapping to omega k plus 3, k2 plus 3 minus the field minus 3 be the Rham of root 10. Okay. And now then some prove that actually each of the two sheaves that appear here, if you want to compute the finite slope decomposition, are actually represented by perfect complexes of amplitude Q2. So these are sort of gives a way to compute this Rham cohomology. Okay. So for example, in the H3, you will have the H0 of this H0 of this first sheaf appearing, and you have an H1 of this sheaf where 1 minus K2 tends to be very, very negative. And thanks to actually work of Denson again, using this complex away from this sort of bad things that you need to invert in order to work on track B, we also have comparison with the classical coefficients. So the classicality result. Okay. Typically, if K you specialize to an integer, which is very, very big, then the cohomology of these two sheaves that I sort of underline in green, they compare very well to the cohomology of sort of usual sheaves that you have constructed from the Hodge bundle. Okay. Okay, and I guess I'll stop here. Sorry, hurrying a bit.
No problem. Yeah, we started later, so no problem. Okay, let's thank Fabrizio for his 2 lectures again. And yeah, maybe if there are some questions. If Fabrizio is not too tired, maybe you can ask questions now, or it's okay. No, I guess probably
we're all tired.
People are tired, so yeah. So we were right not to put more than 2 talks per day then. Okay, so let's thank Fabrizio and maybe George also again.